All right, let's jump right into this explainer and demystify the core infrastructure that allows modern AI to actually remember, search, and use your custom data. I mean, if you've ever wondered how a model like ChatGPT suddenly seems to know your company's private handbooks or code bases inside and out, well, you're in exactly the right place. We're going to break down the exact mechanics of how vector databases use embeddings to actually make this magic happen. So, to solve the massive, and I mean massive, problem of AI hallucinations and limited memory, developers use a technique called retrieval-augmented generation. You'll usually hear it called RAG. Now, the goal here is pretty simple. Ground the AI's response in your actual documents rather than just relying on whatever it happened to memorize during its initial training. Think about it. If you ask an AI a question about your specific product, you want it to retrieve your specific product manual before it even starts generating an answer, right? But how does it find that relevant information so incredibly fast? Which brings us to Section 1, the AI memory upgrade. You see, vector databases are the critical infrastructure layer that makes all this retrieval incredibly fast at scale. They essentially act as a massive, highly searchable memory bank built specifically for language models. But here's the catch. They don't store text the way traditional database does. They actually store meaning. Because to an AI, words are just symbols, right? So an embedding is basically a way of translating that text, or even images and audio, into a really long list of numbers, a numeric vector. Picture a giant multi-dimensional physical space where related concepts live near each other. It's like a giant puzzle. If you map the word dog, it's going to live in a neighborhood right next to puppy and canine, while completely unrelated concepts, like, say, interest rates, are pushed way far away to the other side of the universe. And honestly, this shift in how we retrieve data is profound. It's a real game changer. Traditional database searching relies on exact keyword matching, right? Looking for the exact string of characters you typed in. But because we've turned our documents into mathematical embeddings, we can now use semantic similarity. We're no longer looking for specific characters. We're literally searching for intent and meaning. We're essentially asking the database to find things conceptually similar to this, which, as you can imagine, completely changes the whole shebang for AI. Let's move on to Section 2, how vector search works. To actually make this happen in practice, there's a very specific pipeline running behind the scenes, and it breaks down into 3 steps. First up, we have chunking. You obviously can't just shove a massive 500-page manual into an AI all at once. You have to split the documents into smaller, digestible pieces, or chunks. Second, you take those chunks and pass them through a model to create the embeddings, basically converting those paragraphs into the numeric vectors we just talked about. And finally, step 3, you store them using what's called an approximate nearest neighbor, or ANN index. Now, this is a special data structure vector databases use, so you can search through millions of mathematical records instantly, without having to manually compare your question against every single one of them. So here is a really crucial point. Simply experimenting with how you split your documents often improves your results way more than agonizing over which specific database software you choose. Seriously, if your chunks are too large, the specific meaning gets totally diluted, but if they're too small, they lose all their context. Getting your chunk boundaries right is absolutely one of the highest impact things you can do to make your AI actually seem smart. But as great as embeddings are, pure vector search isn't perfect. Because it focuses entirely on conceptual meaning, semantic search can sometimes just totally miss exact product names, serial numbers, or specific IDs. And that is exactly why experts today highly recommend hybrid search. It's a method that blends the semantic meaning of vectors with traditional, exact keyword matching, giving you a much more reliable path forward. All right, Section 3, the database wars. Having unpacked the mechanics of all this, it's pretty easy to see why this simple math has ignited an absolute gold rush in the enterprise tech market. And the numbers are just staggering. Driven almost entirely by enterprise RAG adoption, the vector database market is explosively growing. We're talking from roughly $2.8 billion right now in 2025 toward a projected $8.5 billion by 2028. That's massive. Analysts are watching this space incredibly closely. And they're actually expecting 2 or 3 major acquisitions before the end of 2026 as the huge tech players look to consolidate the market. Yet, amidst all this explosive growth, you might stumble across some pretty provocative headlines claiming RAG is dead. Kind of like this recent quote from VentureBeat. But hey, don't panic. Actually, scratch that. Definitely don't panic. Retrieval itself is absolutely essential, and it really isn't going anywhere. A headline like this is actually just a signal that the initial bolt-on architectural patterns, where everyone just rushed out to buy a standalone vector database just to try out AI, well, those patterns are being intensely questioned right now. In fact, the biggest architectural debate today is really a major reversal. While vector-native systems like Pinecone and Qdrant used to be the default go-to, a ton of engineering teams are now shifting back to using relational extensions. Specifically, they're looking at tools like pgvector on existing Postgres databases. And why is that? Well, it's simply the lowest friction way to get started. Most teams just don't want the headache of syncing two completely separate databases if they don't absolutely have to. Now, sure, the dedicated vector-native systems are still totally dominating the high end, especially with newer entrants like TurboPuffer that are competing hard on performance, but that's really only for teams that truly need purpose-built systems operating at a massive scale. Moving into our final section, Section 4, the rise of agents. Just as teams are starting to settle down on their architecture, a massive, unpredicted new pressure is emerging: autonomous AI agents. These are systems that don't just answer your questions, but actually take actions on your behalf, and they're quickly becoming major consumers of vector search. But here's the thing: they query very differently than humans do. They issue roughly 10 times more queries in these tight, multi-step reasoning loops. They'll often requery the database over and over again to verify facts before moving to the next step, which, as you'd guess, completely overwhelms systems that were originally tuned for traditional human search box patterns. And because these agents query so relentlessly, engineering teams are being forced to completely overhaul their systems to handle these new infrastructure demands. We're talking about rethinking caching strategies from the ground up, implementing really aggressive rate limiting, and enacting much stricter cost controls. Think about it. If you're paying per query on a cloud vector database, a runaway AI agent could cause your operational costs to literally skyrocket overnight. No one wants that. So we've covered a lot today. We've seen how chunking data and mapping meaning into mathematical embeddings gives AI its memory. But as that query volume is driven straight through the roof by autonomous agents, the game is changing all over again. You have to look at your own tech stack and ask yourself, is your current database architecture truly prepared for what comes next? Will a simple Postgres extension hold up, or are you going to need a purpose-built vector engine? The technology is moving incredibly fast, and getting the foundation right today is really the only way to be ready for the AI of tomorrow.